Thanks, David, for the introduction, and a very good afternoon to everyone. So, I'm here to present our work, Virtual Bricks, which was completed by me and my co-authors, Aryan, Nimita, Vanit, and Shwetank, under the guidance of Dr. Aman Parnami. So, in this session, we have been talking about virtual reality and how it aims to create an alternate reality for the future, for the user. And we have come a long way from the first HMD device developed by Sutherland and his colleagues to the advanced technology that is available in the market today, or the novel research that we have seen in this session so far. And given these technical advancements, it's possible to put the user in any kind of virtual scenario and make him experience that. So anything is possible, and even this. So, but there is a problem that remains, and this figure sort of exemplifies that. So the moment this guy turns around to hug back Leonardo DiCaprio, which actually happened in the movie, he would find nothing but thin air, and he might be disappointed. So the problem is that the physicality of the virtual experience is missing. We can see the virtual world, we can hear the sounds in the virtual world, but there are no objects that we can touch or interact with. And that's the problem that we solve. And it turns out that we already have a great starting point, and that is Lego. A set of mutually compatible construction bricks that can be combined together to create anything physical. From this simple set of chairs, to this spaceship, to this reduced size model of a city. So then we have a solution. So through virtual bricks, we propose a construction toolkit approach of utilizing Lego bricks to create the objects for virtual reality. So over the next 13 minutes or so, I will be talking about our exploration of this, combining these two very interesting things, Lego and VR. Let's start by watching a quick video. Yes. So what happened in this video is that the user created or constructed a bike's handle to experience bike riding in VR. A bike handle that she could touch and manipulate to steer the bike, like we do with a normal bike handle. So before getting into the technicalities of our design, let's look at some of the related work in this area. So the idea of adding physicality to virtual reality has been talked about as haptics. And these systems can be broadly classified into active haptics or passive haptics. So active haptics simulate the presence of a virtual object by applying a force onto the user. So in this video, you see the Omni device, which is essentially a pen that applies forces on the user's hand and constrains its motion depending upon the geometry of the virtual object that the user is interacting with, which in this case, for example, is a skull. So traditionally, these forces were applied physically, but in the more recent systems, researchers have developed better techniques of doing so, like through electromuscle simulation. But irrespective of that, a limitation of active haptics is that they are complicated in their implementation, which limits the kind of experiences that can be achieved through them. So that's why researchers have suggested an alternate approach in form of passive haptics. So unlike in active haptics, in passive haptics, we use actual physical objects or props as proxies for the objects in VR. So this idea dates back to 1990s to the work of Dr. Ken Hinckley, who used props for visualizing neurobiological data. So in this figure, you see a doll's head being used as a proxy for the human brain. In a more recent work, you see how a user is able to use a ball as a prop, as a proxy for flying objects in VR that hit him. So, but as apparent in these two examples, for passive haptics to work, it is important that the shape and size of the proxy should match exactly the shape and size of the virtual object. And that creates a problem. So these are the new accessories from HTC Vive, and they created proxies for 3 different objects that you see in the figure, and like a table tennis racket, a lawn tennis racket, and a gun. And this screenshot is actually from CNET's review of these accessories, which is titled as Too Many Accessories. So the problem is that you can imagine what it would be like if you have to buy a different set of proxies for every virtual experience that you engage with. So researchers have developed many methods to solve this problem, and our paper talks about all of them in their detail. And though they are very good efforts, they suffer from a common limitation that they support only a very limited range of very similar virtual objects or objects that have a similar shape and size. Moreover, the system that you see on the right, due to the use of 2.5D systems or shape displays, they are again complicated in their implementation. So using Lego to create props for virtual reality creates significantly new possibilities. And I will talk about how it doesn't add to any difficulty for the user or the developer. But before that, it's important to consider another important aspect, which is object manipulation. So we just don't touch and feel the objects, we also manipulate them. For example, you rotate the steering of your car to drive your car, or you manipulate it. Most of the passive haptic systems that we have talked about till now allow free manipulation in 6 degrees of freedom. So for example, the doll's head from Ken Hinckley's work can be rotated in 3 axes and can be translated in 3 axes. And same is true for the commodity VR controllers that are available in the market today. But the objects that we face with in real world are not all fixed off manipulatable. For example, a steering can be rotated along its rotation axis, but cannot be rotated or manipulated in any other manner. Simulating such systems with traditional controllers would reduce immersion because the user won't be able to feel the constraints associated with the object. And it turns out that researchers have only recently started to look at this problem. In fact, the only other paper, to our best knowledge, that looks at object manipulation in the way that we do is the work from Microsoft Research at CHI last year, where they added physical constraints between 2 handheld controllers to simulate such object manipulation scenarios. So for example, in case of bow and arrow, you can pull the arrow with respect to the bow, but you cannot manipulate it or move it in any other manner due to the constraints added by the controllers. So what this will do is increase the immersion. To cater to such scenarios, we add special bricks or customized Lego bricks that support linear manipulation and rotation manipulation along a single axis, other axis being constrained. So through virtual bricks, we solve these 2 problems about the availability of props or availability of objects and regarding their manipulation. Coming back to the bike example that we started with, in the video you saw that the user first created a structure for the bike's handle using unmodified Lego bricks. And that's why for our project we call them structure bricks. And then to enable the rotation manipulation required for throttle and steering control, she added 2 of what we call as the feature bricks, which in this case enable rotation across a single axis. So these are all the feature bricks that we had developed, and all of them being Lego compatible can be easily snapped into any Lego construction, as you saw in case of the bike example, hence making it very easy for the user or the developer. All of them provide a different functionality. For example, pose detection, rotation manipulation, linear translation manipulation, and actuated locking mechanism. We also created bricks to support trivial interactions like button input and vibration feedback. So let's look at the functionality of few of these bricks very quickly. So the pose brick calculates the position and pose for the Lego construction that it is snapped onto. It uses an array of IR sensors to scan the tracking signals from HTC Vive Lighthouse system, and also has an IMU on board for finding the pose. A rotation brick enables rotation manipulation along a single axis. So as you can see, these 2 bricks can be rotated with respect to each other, but cannot be manipulated in any other manner in a relative sense. The linear translation brick can be translated linearly across a rail. So the brick 2 can be moved away from brick 1 along this linear axis, but again cannot be manipulated in any other manner. Finally, we have the locking bricks, where the system can be actuated by the computer as well. So the computer can lock the bricks, after which the user won't be able to separate them. And this happens through a servo motor. Otherwise, once the system is unlocked, she will be able to separate them. So how do these virtual bricks work together? So this figure shows our system design. All of the virtual bricks or feature bricks communicate with a central computer running a VR application on Unity through Bluetooth Low Energy or BLE protocol. So all of them create their own channel. We also provide a VR integration package that enables easy integration of the feature bricks and their functionalities into Unity. So now let's look at the design space enabled by virtual bricks. So we define this design space based on 2 important parameters, and that is object type and manipulation type. The manipulation type can be one of the three options. Either it can be free manipulation, as you saw in case of the rotation brick or linear translation brick, where the bricks can be freely rotated across that axis. Or there can be a force resistance to manipulation. So a variant of the linear translation brick is the retraction brick, where the brick can be manipulated, but there is a spring system that pulls back the brick to its original position as and when left by the user. Finally, there is the actuation type, where the system can also be manipulated by the PC. Similarly, the object can be either handheld, can be attached or mounted into the environment, or can be attached on the body to augment body motions. And we will see an example of that. So our paper talks about this design space in detail, but let's try to fill in some of the boxes right now. So coming to the first row and first column, we can consider the fishing application. So in this application, the user holds the proxy of a fishing rod, and she manipulates it to catch the fish. Specifically, she rotates the reel of the fish and also increases its length using rotation bricks and linear translation bricks. And again, this is free manipulation. Coming to the row 2 and column 1, we can consider the slingshot application. So in this application, we have used the retraction brick instead of the linear translation brick, which means that the brick is pulled back to its original position once left by the user. So the user is able to pull the brick to launch objects at the target. And once the brick comes back, it is used as a proxy for a new ball or a new object. Let's consider an example of environment-mounted prop. Here we can look at the disco. So in this video, you see a disco board that has some knobs and sliders, and all of them are implemented using rotation bricks and linear translation bricks. Finally, let's consider an application of the body augmentation, and we can talk about handcuffs. So here we have used the actuated lock brick. So this brick, as we discussed, can be locked by the system, and when that is done, the user can't really move his hands away. But once it's unlocked, he can do that. So simulating that handcuff functionality. So that's the design space, and we have discussed 4 applications in the design space right now. Let's now talk about the limitations. So the Lego is great. It allows you to create a lot of things, but not everything. Specifically, the objects that are of a very large scale are not really feasible to create using Lego. Also, the idea that the bricks are modular, and all the electronics are contained within them makes life easier, because then you can just snap them into the construction. But it also adds problems for the usability of the system. For example, since all the bricks have to form a different communication channel with the computer, it limits the maximum number of bricks that can be used at once. And for a 25 Hz refresh frequency, that number is 15 for the current implementation. Also, since all the bricks have their own batteries, those batteries need to be taken out after some time and need to be charged. Currently, we have 400 mAh batteries in them, and they have a continuous running range of like 2.5 hours to 6 hours for different bricks. The other limitations come from the use of Lego. As I said, Lego is great, but it cannot be used to make everything. And for example, in some of the applications, we saw that the joints faced human scale forces. And the Lego joints are not made to face human scale forces. They will get separated if pulled very hard. So to solve that, while designing the CAD for the feature bricks, we designed tighter joints, and they worked well. But at a later stage, some other better snap together mechanism can also be considered. Finally, talking about the future work. So in future, we are imagining a developer tool which would help the developer to create proxies using virtual bricks. So the user would just need to import the CAD of the object that he requires and mark the axes where different manipulation interactions are required. So for example, in case of a gun, if he requires a linear translation mechanism for reload, then she would mark that with the red axis. And similarly, the yellow arrow marks the requirement of a button for the fire action. Then the system would give you a Lego, like a Lego diagram that would help you put the bricks together. And you can also put in the kind of virtual bricks that you have available with you. So with that, I conclude my talk. I thank my co-authors and specifically Aaron, who couldn't be here due to visa issues. So big thanks to him. And I'm open to any questions.
Hi, hello, my name is Alan from University of Regina, and it was a nice presentation. I have just one question. I would like to know why you didn't use 3D printing instead of using Lego bricks.
So 3D printing, so the virtual bricks were created using 3D printing, but 3D printing has this time that it requires to print. So once you have the bricks, a standard set of bricks that can allow you to create everything, then you can just use them and you don't have to wait for that time to print another brick. So the idea is that these sort of bricks that we have already developed might be sufficient to simulate at least a wide range of objects. For a very specific object, like a spherical ball, for example, you might require to print additional parts. But for most of the objects, the printed bricks would suffice, or Lego bricks would suffice.
Hi, nice presentation. Thomas from University of Bremen. I was wondering, for example, you had the steering wheel, so you can only approximate that. You can't really make a round object with Lego. So do you think that has a negative impact on presence because you cannot really resemble the object that you're holding?
So a great question. In passive haptics, there is a literature to suggest that some mismatch can work and doesn't really reduce immersion. And we have cited that work in our paper. And it talks about, for example, the angles that in their user study was not detected by the user.
All right, I had one more question. Do you think currently everything is built manually? Do you think that there would be value in having an approach that would automatically detect the layout of the bricks currently, so you could on the fly modify them and then they adapt automatically their functionality?
That's again a good question. So that is a different problem in passive haptics, that once you have the props, how do you make them dynamic with respect to the changing virtual environment? And there have been efforts to do that. But for this work, we were considering the problem of creation of props. At a later stage, a different approach can be used to create props automatically.
Very good. Thank you so much. Thanks, Yatin, and please let's thank the speaker again. That concludes the sessions. I'm sure the speakers are going to stick around for a bit, so if you have any more questions, feel free to approach them. Thanks.